So we have one more lab to talk about the material for this lab. And not that we're going to do it today, but I just thought I'd review for a moment what we're going to do. And this exercise here is to write a program that plays tic-tac-toe. And when you approach this exercise, what you should do is not look up the answer on the internet, because there's a lot of solutions to this problem posted on the internet. I mean, hundreds at least. So that will defeat the purpose of the lab. The purpose of the lab is to start learning how to organize your thinking to solve a larger scale application problem, rather than these little problems that we've been doing in the labs. This would be a program that does something completely. It's not just test code for a function that does something. Right? This would be a program that has some kind of application. And so this would be your first application programming assignment. And once again, I want to advise you, don't look up the answer. Just try to work it out on your own. And I'll be talking about a process that you can use to think through this problem. So I'll demonstrate to you the solution of another programming problem. And in that process, we'll kind of look at how you might approach the tic-tac-toe problem similarly. So that's the one last task that we have to do in this class, other than take exam 3. So exam 3 is on Monday. And then after that, we'll review the results for exam 3 and focus on the application programming problem. So with all that in mind, what do you want to do today? You want to jump in application programming topic, or do you want to focus on reviewing and preparing for Monday? Yeah, okay, I get to Monday, right? Monday, right? Yeah. All right, so how do you want to do that? Do you have questions that, because there's a lot of different problems that I don't know which ones you're having trouble understanding. There's some exercises here. And of course we have the lab on binary search and arrays. This exam does not cover sorting, but sorting will be on the final, and we've already covered that topic. So, any suggestions, problems? Does anyone have a problem they want to focus on? And I'll just talk about it, I'll demonstrate it. Yeah?
Number 2.
Number 2 in L6 or E3? Where?
Exam 3.
This one right here?
Yeah.
Oh, is unlucky. And there'll be something like this on the exam. So is this vector unlucky? So the calling code passes in a vector, and the function returns true or false, a Boolean value. Returns true if the vector is unlucky, and returns false if it's not unlucky. That doesn't mean it's lucky. It's just not unlucky. All right, so let's see. I'll do this. Say exam 3. So implement this function. Let me show you what it would look like in the exam. All right, so this function would be listed like this. And you can repeat that function declaration if you want. Otherwise, just provide the body of the function. Now, there's no such thing as an unlucky vector, right? I mean, it doesn't. But just for the purpose of the problem, we have a definition. So you have to read and understand a definition. And I may, if I ask this problem on the exam, then I may change the definition of what unlucky means, or lucky. Right? It's just a make-believe problem. So let's see. Implement a function that determines if the unlucky number 13 appears in a vector. The function returns true if 13 appears in the vector at least once, otherwise it returns false. So we just have to look for the number 13. So we need to scan across the vector, so we need a counter, I, in a loop that takes on all the values, all the valid indices of this, of the vector, the argument v. So I starts at 0, and it must be strictly less than v dot size. If it hits v dot size, its position is one past the end of the vector because we start labeling from 0. So as we scan through the vector, if we find at position I the number 13, we return true. It is unlucky. We don't have to look at any other positions. If we found 1, we're going to conclude right there on the spot that the whole vector is unlucky. If we complete the loop and never hit that return statement, it means there's no 13 in the vector. So at that point, we know that it's not unlucky, so we return true. So that's how your answer might look in the exam.
Yeah, return false.
Oh, sorry, got that wrong. Thank you. False. It's not unlucky. Let's take a look at some others. Write test code. Let's write test code that tests every statement in the isLucky function. Mainly, when you get that type of a question, you want to test that a case where it returns true and a case where it returns false. Because this is a substatement of the if statement. So we want to execute every statement. So we want to execute this statement. We want to execute its parent if statement. And we want to execute all the substatements. So there's a substatement. Here's a statement. We want to execute all of these. We want to execute the for loop, which obviously any invocation of the function would do. All right, so we need to create a vector. And then we need to populate it with values. I'll show you a minimal test satisfies the criterion in the problem. So push back, say 3. And then we assert that is unlucky.
This vector has to be put into the main function?
We don't need, I'm just showing you what would be acceptable in the exam.
It would have to be.
Yeah, you don't need to state that it's in the main function. Yeah. Is unlucky is false, rather. Yeah, so this is false. So pass in this v, and then it's not unlucky because there's no 13 in it. But if we push back a 13, and then now the vector has a 3 and a 13 in it. Here it only had a 3. Now when we assert this should return true. So that's an example of a minimal test. But it executes every statement in the function. Is strictly increasing, are identical. Let's see. Let me look at let me do another problem here. So let's implement another function called isLucky. Let's implement isLucky. So isLucky returns true if V contains at least one 7 and no 13s. So this is a little bit more complicated. Here we just return true if there is a 13. But here there's two values that are of interest, 7 and 13. It should have at least one 7 and no 13s. Can you do this one on the exam without your notes? Okay.
Would be a nested loop.
I think there's something like this on there. So this is a little simple compared to what I think I put on the exam. It was a while ago I made the exam, but I think I have something a little more complicated like this.
Would you have 2 loops?
Huh?
Would you have 2 loops then?
2 loops? We can think about it that way. The first loop would
Look for the 7.
check to see if there's a 13.
Yeah. There's
Yeah, that's a good idea. Let's try that. Let's try that. So the first loop checks to see if there's a 13. And if V of I is a 13, then we know right there on the spot that it's not lucky. We found a 13. Shouldn't have any 13, so we've done that. Now we have another loop. That checks to see if there's a 7.
You can do not 7 and return false.
Let me ask this question. Because someone would do this. I'm showing you a faulty solution here. See, whenever you see this, you should immediately be suspect here. If this is not true, then we're going to do this. That means we're going to return in either case. Well, why have a loop? If the very first statement returns, we're only going to do the loop for I equals 0. You see the problem? So we always return on the first iteration. So we know that that's going to be that's an error. It wouldn't make any sense to have the loop. Then we just have V of 0. We're just checking V of 0. So we know that if we find us, we already checked, there's no 13. Now we're going to check to see if there's at least one 7. We found a 7, we're safe. We can return true here, right? But this answer is not, this only gets partial credit on the exam. What's missing?
You have to return false if it doesn't have a 7.
Yeah, we got to return false. So where do we do that? If it doesn't have a 7.
When it finishes,
Huh?
when it finishes the loop.
Yeah, exactly, exactly. When it finishes the loop, it's not lucky. We didn't find a 7. It didn't have a 13, which is good, but it doesn't have a 7, which is bad. All right. So that's, I've never solved it like this. So, that's a good solution. It's a nice solution. let's look at another possible solution that you could use. I think I probably would have done it like the following. I'd use a loop. And I'd have a variable found 7. Do we find a 7? So if, I'm just going to copy this. If we find a 13, we're going to return false. If we find a 7, and then we're going to set found 7 to true. So we look at every value. Rather than having 2 loops, just stick with 1 loop is enough. But we have to keep track of whether we found a 7 or not. But as soon as we find a 7, we can't stop looking because we've got to keep an eye out for a 13. So we've got to go to the end of the vector, see if there's any 13s in there. Once we get to the end of the vector, if we didn't find a 13 and therefore didn't return from the function, then then we just have to look at the variable found 7. So if found 7, if we found a 7, we're going to return true. Else we're going to return false.
Can you just return found 7?
Yeah, I was just going to do that. Thank you. A good suggestion. I'm trying to make it readable. So this is the verbose version. Here's the quicker version. Oops, rat turn. Getting sloppy. It's the same thing, right? Just return found 7. If found 7 is true, return true. Otherwise, return false. Well, it's the same as return found 7. Good enough.
Can you do it without having to have a variable?
Without this,
Yeah.
I think you have to have a second loop in that case.
So if you were to take the variable out and your second if statement was if not 7,
If not 7, return.
if v of I does not equal 7, return false. Because then it would check it in both cases, wouldn't it?
Hold on there.
Still have to search for 13.
So
regardless.
instead of this, to do what?
So you still have that first line, and then you have a second line that's if v of I exclamation point equals 7, return false. And then outside, just return true. Would it check both in that case?
And then just return true out here.
Yeah.
Get rid of that. Let's look at that one.
Well, you run into the same problem. You check the first and then you'd be done.
Yeah, let's suppose 7 is in the second slot and not in the first slot. Let's suppose we have a 2 in the first slot. V of 0 is 2.
Gotcha.
And then 2 is not 13, so we don't return false. 2 is not 7. I mean,
Yeah.
so we return, what was this, return true? Oh, return false.
Yeah, I see what you're saying. Yeah, it doesn't matter.
So we want at least 1 7. So that's not going to work.
Can you nest if statements like you do loops?
Yeah, you can nest if statements. Let's see. Do you think we can benefit from nesting here?
Well, I would think if we took if 13 and said return false, else check if it's 7. So, well, if it's 7, you can return true. Otherwise, you'd have to go through the loop again.
Well, what if it's 7 is in the first slot and 13 is in the second slot? then you're returning true because you found 1, 7, but you didn't check for all the 13s. It's good to probe these other other solutions. It's very good to probe these things. This should be something like that, right? Which one's simpler to look at? This one? Or this one?
The first one I'd be.
Well, I think it's subjective, isn't it?
Yeah.
So you decide. You'll get full credit for either of those. This one is slower. I mean, this one is faster than the other one, especially if V is large. Because here, in this solution, we have to pass through V 2 times. Here, we only pass through V once. So V is large. And the 13 and the 7 are near the end of the vector, then we're wasting time. All right. How about this one? Is strictly increasing. Want to look at this one? Yeah, okay. Let's go through these. Is strictly increasing. Oh, and we have an example here, see? -2, 4, 5, 6, 8. This is strictly increasing. This is not strictly increasing because we have 2 6s next to each other. So it's not strictly increasing. I call it non-decreasing. So let's modify the problem. Let's make it strictly decreasing. Let's solve that problem. Is strictly decreasing. So what we need to do is look at neighboring pairs. Let's look at an example. This is strictly decreasing. So we would have, say, 13, 11, 7, 2, -1, -4. How do we know that that's strictly decreasing? Just how do you do it in your mind? You look at each value and say, is this one bigger than the next one? Yeah. All right. Is this one bigger than the next one? Yeah. You see how you do that? You see that each time you go forward 1, you're dropping. I guess there's some different ways of doing this. So we're going to need a loop. Start from somewhere, some kind of limit, an increment, or decrement if we're going down.
Would be an if statement. If
Yeah, we're going to need an if statement, yeah.
BI is greater than BI plus 1. Continue the loop.
Like that.
Yeah.
That would work. But that can be, whoops, fixed. I have to fix this. Thing is that, why don't we do it like this? See, that's in the sort in the positive, right? So you can do it like that. But here's another alternative. If we look for the negative case, this is the positive case.
Yeah.
if we look at the negative case, that vi is less than or equal to vi plus 1, then we return false. So, I mean, this is how you thought of it, right? So maybe that's the most readable. But this is shorter. Here we're looking for the positive case. If things are okay, let's continue with the loop. Otherwise, they're not okay, and let's return false. So that's how we would think about that. This one says,
Things are not.
is there something wrong? Yeah? Oh, return false. Otherwise, we don't do anything, which implies we're going to continue with the loop. You decide which one you like, because they're both full credit on the exam. So, whatever is easier for you. Some of the most readable to you, because readability is the name of the game. Most computer programming problems don't have to do with efficiency. They have to do with readability. Most of them, 99%, maybe higher than that. Occasionally you're hit with, oh, I got to write an algorithm that's efficient. But common programming tasks that the multitude of programmers are dealing with day to day, I would say the vast majority of them are readability problems and not efficiency problems. Anyway, these are roughly the same in terms of efficiency anyway. So which one's more readable? How many people think this one's the most readable? How many people think this one is the most readable? Oh, that one wins. Okay. All right. Let's delete that then. All right. So what else are we going to talk about here? How about let's go back to.
Well, you didn't finish the other one because you didn't talk about where you started and finished the loop.
Here? Oh, we didn't finish this. We never, well, I know we didn't finish it because we only returned false. We never returned true. So where do we return true?
If you finish this.
End of the loop.
Yeah, when we finish. Because we didn't find a bad pair. And I'm always doing this. We didn't find, a problem pair. Well, of course, we need this. Now look, we start, I is going to have to be 0. We're going to start with 13 and compare 13 to 11. So we know that I needs to start at 0. But how high do we go?
B size minus
Well,
1.
we get to -1 and we compare -1 to -4, right? So I gets to -1. But we don't want to set I to -4 because there's nothing past -4. So that we'll get a memory exception there. We're going to try to access, our code will try to access memory that's not part of the vector. So either it'll quietly, continue executing, maybe incorrectly, or else we'll get a memory exception. So I has to stop at this value. This is the last position here. Normally, if we want I to stop in the last position, that's size -1. So we write the loop, normally I less than v dot size. That means I, the last time that the loop runs is when I is 1 less than v dot size. But we don't want to go all that way. We want to go 1 before, so we just subtract 1 there. Or you could do it like this. I know this might be more readable for some of you. I is less than or equal to v dot size minus 2. This is v dot size minus 1. This is v dot size minus 2. It'll have to be less than or equal to in that case. But you wouldn't see it written like this normally, in a textbook. Or in an example of code on the web for that matter. It's just not normally written like this. So it's useful to follow convention because then it's easier to share code and understand other people's code. All right. What are we going to do now? We finish that. Say in here. We need to work with arrays. We need to work with two-dimensional arrays.
Is exercise 5 gonna be on the exam?
Exercise what?
Exercise 5?
5.
Yeah.
This could be on the exam, yeah.
Can we go over it?
You want to go over this? Okay. Counting occurrences. We get a vector v here. And we want to know how many times does the integer k appear in that vector v. Oops. All right, let's do this one. How many times does k appear in v? So if you can think about, it really helps to just jot down an example. Let's suppose that k is 7 and v is 3, 7, 2, 6, 7, 8, 1, 7, 0. That's just an example, just so you can think about it. So how are you going to count how many times 7 appears in V? You have to look at every number. We'll look at the first one, and then we keep track of it. So I'll use my hand here as a counter. I got 1, that's 1. No, no, yes, add 1. No, no, yes, add another 1. No, I'm at the end. Oh, 3. So that's how you would do it. And so let's write the code for that. Well, we have that counter. Remember, we have that counter. We set it to 0. When we start this, we say, okay, my hand has, I'm holding up my hand here, and it has no fingers out. And so that's a 0. So you have to initialize your counter to 0. When you hit the first one, you increment the counter. So we need a counter. Initialize to 0. We need to scan across the entire vector. If we find one, we find a 7 or a k, let's do it for the general case. If we find k in position I, then we increment our counter. Partial credit for that answer. You only have I'll take a few points off for this one. The problem was worth 25 points, it would take off 5 points, probably. What's missing?
Return your count.
Huh?
Gotta return the count.
Exactly. So you got the main idea down,
Then we return.
but you need to return the counter.
Let's finish.
You have to finish it here. So you got the main idea, you got the algorithm. So you would just lose a few points for that one. That's not that's. But you should I want you to keep in mind you're in the context of this function, and it returns an int. It's like if you're returning a bool, you have to return true. And think about that. We caught our mistake here because we saw we only returned false. We didn't return true. We need to return true and false here. All right, that's that one.
So would we be wrong on a problem like that if we C-outed?
Yeah,
counter?
yeah,
Okay.
yeah. Because that would write a function that prints the number of times k appears in V. So, and then it would return a void in that case. So that would be wrong. But you would get partial credit for that to show that you knew the algorithm. All right. How about working with flatten or identical. I can't think of other. Well, here's the algorithm. Append vector. Maximum. They all seem so easy to me. I know it's hard for you, right? Every quarter they get easier and easier. What do you want me to look at or talk about? Or we can break if you don't want to do any more work. What do you want to do? Is that enough? I'll tell you right now that the exam will have a few problems, probably, and I don't remember it exactly, the exam. But I always make the exams the same way. There's a few problems that are exactly from the labs or the practice exam. And then most of the problems are a variation of those. And then there's some problems that are unique, but they fit in with this class of problems. And I get students that they take the exam and they say, you didn't cover this problem. You know, but I mean, it's in the same type of problem. You have to iterate through the vector and you're looking for a 16 instead of a 13. I know, something like that. Or you have different logical operators that need to do something different. So, you know, you can't just memorize the solutions to these. You've got to sort of figure out, you know, how to solve these problems generally. Let me talk about the binary search before we finish here. I'm going to talk about the variance of binary search. First of all, what is linear search? Yeah, let's do, say we have an array A of size. And let me just do these for you. Here's one. Linear search. This one should be easy for everybody. You want to find a value k in A, where A has size, and return the position of k in A. Return the position of k in A. Well, return the position of the first occurrence of k in A. Because what if k appears multiple times in A? So let's be more precise about it. Let's return the position of the first occurrence of k in A. So here, I is less than, maybe I won't use size here. Let me use n here. So n is the size of A. N is the size of A. So we look through here, and if we find k at I, then we return what? I. That's the position of k and A. That's partial credit right there. What's missing?
Return -1.
Yeah, return -1. And we would have to put that up here in this function. We'd have to add that to the definition of the function here, the statement of the function. But this is the convention to return -1. What about linear search? Oops. How about linear search just says, you know, is K an A? We're just going to return, instead of returning the position of K and A, let's return true or false. Let's return true if K is an A, and false if K is not an A. Does everyone see this? This is easy? Easy, right? So instead of returning the position, if we find K and I, then we're going to return true. We found a K and A. Otherwise, instead of returning -1, which designates that we didn't find K, we're going to return false. So that's the other sort of form of this problem. And the other two forms are, instead of, oh, sorry, this should be, sorry about that. This is an array. Instead of an array, do it with a vector. So you wouldn't pass in the size, you'd use b.size in that case. All right. Now what about binary search? The same thing with binary search. We have different ways of asking for that problem. Let's do it like this. Assume the values in V are not increasing. That's the problem we solved already. Decreasing. Assume the values I can't even spell it now. Values. What am I doing? Did I spell that right?
Yes.
Values?
Delete the first S. The first S.
Oh yeah, I can't believe I totally lost how to spell values.
There's a reason we're not English majors, it's okay.
Huh?
So there's a reason we're not English majors, it's okay.
All right, so assume the values in V are decreasing. Return true if K is in V. Use binary search. There we go. All right, suppose that's the problem. So we have a Boolean return value. And we have a vector of int b, and then we have k. Is k in v? V is decreasing. So we're going to start at the two endpoints and then sort of keep, and that's our initial range. And we keep chopping that range in half. Either we move the left-hand side to the right or the right-hand side to the left, and we keep making the range shrinking. So we have a start index for the range, which is 0. We have an end index for the range, which is v.size -1. Some algorithms start, they use e to be one past the end. And, but for this problem, the code is more compact if you set e to the last index. And then we have a loop. Remember, there was something, this is just from memory now. Well, s is less than or equal to e. And we're going to do this loop. Well, the start of the range is less than or equal to E. It can be equal to E. So that means we have to look right there on that spot, at S and E. Then we compute a midpoint, M, which is just the average of S and E. That's how you compute a midpoint. Take the average. And then we check to see if what's at the midpoint is what we're looking for. We're going to return true. We found it. Else, if what's at the midpoint is less than K, what are we going to do? Else, and I'm not going to put a test in there, but that's because it must be the case that V of M is greater than K in that case. What are we going to do? I don't need that. And if we finish the loop and we never return true,
Return false.
yeah, return false. We didn't find it. So what happens in this case where K is bigger than the midpoint of the range? Now the thing is decreasing, okay? So V of S is bigger than V of E. What was that? Yeah, oh, the ending? Okay. Now, I don't know if that's true, but I think it's true. The ending value to the midpoint. Wait a minute. Isn't there like some kind of a plus minus thing in there as well? Because we didn't, remember we analyzed this before. We already checked the value at n. So what we want to do is set the n to 1 before the midpoint. We're going to squeeze the range a little aggressively. We already checked it at m. We know that V of m is not K. So we don't need to set E to m. Let's set it to m minus 1. But let me check to make sure that this makes sense. Do we want to set E to m, or do we want to set S to? The other choice here would be that we move S up. Now we have the case, S, so it's decreasing. So I'm just putting a note here. So V of S is bigger than V of E. So I have to think this out. I got to verify this in my mind here. So V of S is bigger than V of E. It's decreasing. So if V of M, if K is bigger than V of M, how do you figure that out? If K is bigger, how do I say this? If, let me do it like this. If K is bigger than V of M, maybe that'll help me. So if K is bigger than V of M, that means, don't we have to bring this up? Oh no, that's because it's decreasing, right? So we're going to go the other way. Huh?
The bigger values are at the beginning of the vector.
Because what?
The larger values are at the beginning of
The larger values are at the beginning. So, so that means we would bring E up, right? We would bring E down to M. So I agree with that. I can't explain it that well. It's, you just have to think through it there, right? Let me do it this way. Let's be absolutely clear about it. So we have 13, 11, 4, 1. Let's suppose that's the vector. And let's suppose let's suppose that M is in the middle now. Suppose that S is here. M is here, and E is there. And let's suppose that K, let's see, K has got to be bigger than V of M, so it has to be bigger than 4. So let's suppose K is 7. All right, there's our example. Here's a range that's decreasing. And this could be inside the algorithm somewhere. It may not be the complete vector. This is at some point in the algorithm. This is what the range looks like. And this is what E is referring to 1, and S is referring to the position where there's a 13, and M is referring to the position where there's a 4. So that means it's to the left of M. So K is to the left of M. So what we want to do is leave S alone and bring E just before M. So we know it's not at M. We checked it up here. We checked it here. We know it's not at M. So the next point we want to check is the position right before M. All right, now that I do the example like this, and I think it through like that, now I feel really confident I got it. And before I did this, I was just sort of trusting that you got it in your head right. But if you can do all of this in your head really quickly, that's great, right? But on the test, maybe you're a little nervous. And you want to just sort of write it out like this and convince yourself with an example that you got the logic right. All right. Get rid of some of this junk. So that's it. Well, what happened if we changed this prob statement and instead we made it, we wanted to return the position of K, not true or false? Well, this is very easy. We just return, instead of returning true, we return M, that's where we found K. And instead of returning false, we return -1, because that's the convention. And what about the case where it's not a vector, but it's an array of int? Now what do we do? Yeah, just do everything the same way. We just edit this. It's all the same algorithm. This is all the same. Look at that. That's it right there. Pretty straightforward. That's it. Those are all the variations you have to look out for. There's nothing else I can think of to ask for binary search. Well, there is another problem there. What was it? Guess the number game. That's like a game to play to do binary search. Can you code that up in the exam? That's not that hard, right? You take a look at that. Make sure you know how to do that. And I think that's it. I think you're all ready. Well, you should all be able to get an A on this test, right? All right. Question?
When I came up with my the solution for the game,
Yeah.
the solution was the answer is 1,023. If I was putting 1,022.5 or any number with a decimal, it
Yeah.
would keep listing that number and keep listing the word too small.
Well, because you're trying to read in an int, right?
Right.
And you enter in a decimal value. So it's there's a problem with the input.
So if I
You,
do
if you
that,
declare it a double, then maybe the problem would be fixed. Yeah. Do you want to look at this one? I mean, this is pretty straightforward, right? That one there? You want to look at that? Or just call it quits? How many people wants to look at this? 2. That's not enough. I'll talk to the 2 people individually. All right, we'll call it, that's it, we're finished. And the 2 people that want to discuss this, you can stay after, we'll do it now. Do you have your code for me to look at?
No, I